Welcome back to Calculus1.
All right, there we are back. Part 2, then part B of the problem. So the problem was this square is losing its area, it's shrinking. And two-part question. First part asked for the change of area, and the second question is asking for the change of diagonal. Now, you might not know the area, the formula for diagonal of the square off the top of your head, but you can use Pythagorean Theorem to figure it out. It's not the end of the world. So, the length of diagonal d squared is equal to a squared plus another a squared, because it's a right triangle. And we have that the d squared is equal to 2a squared. From where, when you square root both sides, you get d. We don't need plus and minus because these are lengths, so it's always positive. We get a root 2, right, when you take square root of both sides. So there's your formula for diagonal, and then immediately you differentiate that in respect to time to see how fast is it changing. As soon as you get the equation which contains the question, the variable that is in the question and the variable that is given in the text of the problem, you can hit it with the derivative to connect the two to get the related rates. So now we have the d dt is equal to root 2 dA dt, right? Because the derivative of a is 1, and then you follow with the chain dA dt. Root 2 is a constant, you just copy. So now I have my related rates. We know that the side changes with 1, right? Negative 1. So the rate of change of diagonal is square root of 2 times negative 1, which is just negative root 2. So the diagonal in time changes as negative root 2 meters per second. Because the d, how do I know these units? It's d. d is the distance, the length of the diagonal. And that's measured in either meters or millimeters or feet or inches. And then I have divided by time, because the problem had earlier seconds and meters. I'm using meter per second. Your denominator, as you can see, is always just a second or a minute. It's never squared because this is the first derivative. It's dt. Right, Chewbacca? So we have the change in diagonal, and that's the answer for part B. Let's see. What else can we do that it's really, really cool? All right, that's spicy. That's for later.
Wait, no, let's do it now.
Yes. You stretching? Yeah. All right. All right. That's stretching. You're gonna fall asleep. Huh? One of the interesting problems in the textbook is the spreading oil. Right, the oil rig started leaking oil into the ocean. So you can use this to figure out some environmental crisis. But it doesn't have to be just that, guys. It could be a forest fire that is spreading around. It could be the virus that is spreading in a certain area. You have to quarantine that, right? So you're looking in the ever-growing circle of people that are getting in touch. The other people, they cough and they sneeze, and then these guys are now sick. So it's not just spreading oil. When you have a concept that spreads in one way, it's going to be the same if it is any other concept that looks pretty much the same is going to be modeled the same way. So they say the oil is leaked, right, and in a column C, and then it's spreading in a circular patch and then they want to know the stuff. Well, the fire has to start somewhere, and it's going to spread. Fire doesn't go in a straight line, right? It's going to go and grow again as a circle, bigger and bigger and bigger and bigger. So you can figure out a lot of different things that will be happening at the same time. So what do I have? I have this oil rig, right? And then I have these concentric circles of, right, oil spill getting larger and larger and larger as the time goes on. So what is happening here? Well, we know that the area of the circle is pi r squared, and then when you hit this with the derivative, you get the related rates, which connects the area of the spill with the radius of the spill, and all of that is happening in time. So as the radius grows, we can clearly see that the area grows. But we just want to know how fast it grows so that you can set up the cleaning crew and all of that needs to be done. So the a dt is going to be 2 pi r dr dt. So the derivative, well, pi, we copy the pi. Derivative of r squared is 2r. And then we have to follow with a chain because we took the derivative with respect to time. But we took the derivative of the area and we took the derivative of the radius. Now, again, be mindful of the letters and which are the variables and which are the constants, because pi is the letter. That's a Greek letter, actually, p. That's the equivalent for equivalent letter in the Greek language. So pi is just, it's still a letter, but it's a constant. And since it's multiplying to r squared, we get to copy it. If it was pi plus something, then the derivative of pi would be 0. So in this case, we have a derivative of r squared is 2r followed by the chain, and then we have the pi in the mix, and we have all of this here, which is related rates formula. So now what I do with this is I plug in the values and I calculate everything that needs to be done. So it says the radius of the oil patch increases at the rate of 30 meters per hour. So the change in radius in time is 30 meters. So none of these over here are for decoration. They're all doing something. We'll take a look. Hopefully next example will make more sense for this. So now the a dt is the change in area, which is what you're looking for. You have a 2 pi, right? And then the radius is 100 meters, and then the change in radius is 30 meters per hour. And now you multiply these things, you get 6,000 pi meters squared per hour. The longer you delay the cleanup, the more you have to clean up, right? Because you see how many, 6,000. No, it's just exact over there. They were good. All right. Anyone? Yes. No, that was just a random example from the. It was example 1 done in the book. Now I have the next type of a problem. So what we have is the rate at which two airplanes are going to approach each other and how fast the distance between them is closing. So if you think about this, you have an airplane here, and then you have another airplane here, and they're going towards each other. You see that there is a distance d in between them. And you see that as these two airplanes are getting closer, the distance between them is closing. If they both end up at the same point at the same time, it's called a collision. Right? Well, I need to give you the definition. So, how fast is this distance closing if we know the speed of each airplane and how far apart they are? Let's say there's an airport over here. All right. Observe my runway, like none of these can land the way they are, but that's okay. They can drift in. So let's see. Yep. So if you look at this one over here, there will be a rate at which this airplane goes. Let's say it's dx dt, because that's the x direction, horizontal, right? Dx dt, and let's say that the speed of this airplane is 500 miles per hour. And let's say that this guy over here must be dy dt, right? Is going to be, let's say, 550 miles per hour. The change in distance in time is equal to what? So which mathematical rule we are to use to come up with the equation that will relate x, y, and d? We all understand that this distance over here is x, this distance over here is y, and then there is the distance d in between them. Which formula relates these three? Pythagorean theorem. If that's 90 degrees right there, x squared plus y squared is d squared. All right, are we good? So now, differentiate, right? Differentiate in respect to time. So this is going to be 2x dx dt plus 2y dy dt is equal to 2 dd dt. 2d dd dt. I'm not sure which one you're asking. Oh, hell yes, that's the whole section. Because look, those numbers are given to you, right? Those are variables. That's what you're plugging in.
You can't just say 2y. Like after you take the whole derivative.
But see, this x is the distance, and the x dt is the 500. If you don't write it, where are you going to plug in 500?
Yeah, okay.
Plus y, and then we have 550 is equal to d dd dt. So now if you know how far, and you know that, right, if you work the air traffic control, you know how far each of the airplanes is. Let's say this one is 100 miles away, so x is going to be 100 times 500 plus, and let's say y is 200 miles away, so that's going to be 200 times 550 equals to, and now d. But look, if this is 100 and it's 200, you can find d by Pythagorean theorem. So 100 squared plus 200 squared is equal to d squared, and then you have, yeah, 10,000 plus 40,000 is equal to 50,000 equals d squared, and from there you can get your d. So how much is d? 100 root 5, right? So that's 100 root 5 dd dt. So how fast are two airplanes approaching each other? They are approaching each other when you calculate all of this and divide by 100 root 5. That is the speed at which they approach. That tells you how much time you have to react. Right?
Probably have more time if you can calculate this.
Do I?
We probably have more time if you can calculate this.
Actually, I have something for you since you're making that. So that's gonna be 1,000 plus, that's 110. So we're going to have
extra zero. That's 110 million when it's 110,000 is what you want.
it's a 50,000 and 110. Do I have a million?
Yeah, you have an extra
No,
zero.
it's supposed to be like this. Oh yeah, I do. Oops. 1, 2, 3, 1, 2, 3. Okay, cool. Thank you. Oh, but I had this right. There we go. And now, finally, the change in distance in time is 5 into 16 goes 3 times, and then 2. And then another 0 root 5 miles per hour, or whatever the units were. So that's how fast the distance is changing between them. Let's see, Brian, this is, you want to work
As a flight attendant, yes.
as, no, air traffic control. Let's check it out. There we go.
That's right now?
Yeah, this is live. So you can see this is all live feed, and it's for the entire world. So as you can see, if you are trying to come up with you've seen what a calculation is between two planes, right? So do you think that someone sits and calculates this by hand? You know what your job is? Your job is to write a source computer code that's going to untangle this. That's going to run calculation that we just see of how fast two airplanes are going to approach, which heights, which one, right? Who goes first to land, right? Humans don't do this, right? Software that you write does this. You have to learn mathematical formulas. You have to learn the concept of the related rates to understand, to program something. Then you learn a programming language and you program this thing. Computer will deal with this mess, right? So when you are Okay, so this is France and Switzerland over here. I'm from here, and then right here.
It's covered by letters, so you can't really
Like
see
this
it.
wing over here, like this little. Right there, that's what I was born. Right there.
I can't even see the name.
So, so you see how busy this is. Here's the United States, and
That's crazy.
boom, right? And then, you know, you can. Do they still have it?
Professor, I come out of Princeton Airport.
Yeah. So that's the view. For each individual plane has also the view from the plane. Yeah.
I feel like this is a video game. That'd be so
It is.
Oh, let me see.
So those are known and estimated positions, right?
They're known, not estimated. Known.
Well, I just assume that some of them would have to be estimated because there's
The-
what are the chances of, say, a plane outside military and civilian radar with its transponder off? You pretty much have to mathematically guess where it is.
Yeah, well, those are the rare cases. But as you can see, guys, I just wanted to show you that you have these. You have to do these calculations somehow, and you've seen the interaction. So when you start building something, you start with the two interacting, then you add another one and another one and another one. You develop the whole matrix grid on how to track everything in that case.
So I can translate the plane.
Yes, it's live. It's live. So I actually use this every time when I'm going to pick up someone. I don't go by just use the website. You click on the plane and just keep refreshing. So
That's crazy.
That's that. So you've seen the calculation done for two planes, and obviously over there you have tens of thousands. So go and figure out all the routes and heights and everything else, and then manage that. So that's the related rates for you.
Do you have to pay to get all the info? Because a lot of them have a lock button.
Yeah, you have. They have a paid membership. I don't have a membership because I don't need it, but yeah, you can pay, and then they will get you more. They don't trace military planes and president's plane, but they trace. Yeah, but they trace all the commercial. I'm not sure that maybe commercial planes. I think it's just passenger stuff.
I mean, if you need a bet on it, Trump's probably at his golf course.
No way.
All right, let's see.
You could probably calculate the flight route.
Yeah, probably.
Only use the military plane as well.
So this is how it looks like. The problem which I just discussed also is discussed with different numbers and stuff in the textbook. So you can read that as well. I will address that. Ooh, this one is a cool.
How much time are you giving us for labs? Like today?
The rest of the class. But we have to do maybe 3 or 4 more examples probably. All right, so the next problem. Generally, when I teach Calc 1, I go and I find one of those shaky rocket launch videos where either SpaceX or someone or NASA is launching a rocket, and then the video is all shaky because they haven't developed the system to have the automated camera do that. They have a Joe somewhere on the side standing and holding the camera and shaking. So I want to design a system that will actually have the rocket at all times in the shot. And I want to see what kind of mathematics is behind that, because I actually have to program the computer to adjust the angle of the motor. Well, I'm sorry, the motor will adjust the angle of the camera so that the rocket is always perfectly in the center of the shot. Now, let's see, usually stationary cameras or a person doing this, where you can design something very simple.
Yeah, so I think that's the only way to catch it on this thing.
If they watch my stream, they probably would.
One issue is to know the speed of the rocket, you first have to launch the rocket. So
Exactly.
So
Here's the rocket right here. Look at that thing.
But if you want to
Says USA and everything on it. All right. So we're going to launch the rocket to the moon. All right. The rocket is going to shoot straight up with the dh dt. So the speed of the rocket is going to be dh dt, because the speed is the distance in time. So the height is actually distance covered, and that happens in time. Now over here in this little nook, I'm going to have a camera set up, and the camera is going to have, right, some angle, and this angle, call it angle theta, is going to change, right, which will change what we call the angular velocity omega, in physics called omega, but we know this as d theta dt. So change of angle in time. If this is the camera lens, guys, this is what we need to design. That's what we're designing, right? So you see that it's changing the angle of the camera. And as the angle is changing, the question is, at which speed? Is it a constant speed at which it's changing? Of course not, right? Because when the rocket shoots, it has to go fast at the beginning, and then as the rocket is far away, right, it's going to be very small. By the way, that's how they hijack the planes. When they're far away, they're very small, so it's easy to take, right? They do the same thing in Despicable Me. They take the moon, right? Because when it's very small, you can, yeah. So what happens is you adjust the angle, right? But you have to start moving faster, and then the camera has to slow down. What is the mathematical formula for that motion that you need to program into your Arduino that controls the servo that will move the camera that way?
What if you also want to calculate how the camera's zoom constantly keeps the rocket in frame? Would that be like Calc 2, Calc 3?
No. The zoom is done by the lens. That has nothing to do with... we are just trying to have the thing in the shot. As long as something in the shot, the lens will do the zoom. So that we don't have to worry about that feature exists, right? Every single camera has the autofocus, so that we're all cool with that. It's just we're trying to eliminate the human so that the shot is steady. So you have a motor move, and the motor will do the perfect job because it will be tied to directly to the speed of the rocket. All right, guys, so at some point, right, the camera will be looking up, and I hope that all of you see the right triangle here, right, the red right triangle. So when you have a triangle, you have few concepts to think about. There are concepts of area and a perimeter. We don't need them here. There is also the Pythagorean Theorem. We don't need it here. Well, we'll need it, but later. And then there's also trig, right? So what do I need to relate? Let's say this is 500 feet over here. That's, let's say, a standard distance. You don't have to worry about that. But obviously the height will depend on where the rocket is, and then the speed of the rocket as well is there. And then you have the angle theta. So if you look at this, you have the opposite and the 500, so that's tangent. So you start by writing tangent theta is equal to height over 500, from where height is equal to 500 tangent theta. Maybe I should write this. I'm going to write it underneath. It doesn't matter. So height is equal to 500 tangent theta. So now I'm going to take the derivative, and I get exactly what I need. dh dt is the speed of the rocket, is 500, and then derivative of tangent is what? Very good. Followed by the chain rule. So look, this over here is what? Oh, sorry, we're solving for the, so this variable here is that omega, angular velocity, that we're looking for. So d theta dt is equal to dh dt times 1 over 500 secant squared theta. Now secant squared theta goes on top and becomes what? Very good. So we have cosine squared theta over 500 dh dt. This is the related rates equation that you were after. You have all of this information at all times. So you can, so this over here is the omega, which is the angular velocity. This is what you need to program in, right? Because that will tell motor how much to spin so that the camera has the shot. And then you have the angle theta, which you can always measure. And you also have the speed of the rocket over here. You have that as well. So you have the angle, you have everything. So now if I say that the speed of the rocket is so and so, you plug that number here, and then for each angle, you know you want to have a continuous, right? You start at 0 angle, and then you end at whatever, 60, 70 degrees, right? By that time, the rocket is pretty much not in shot. So when you look at this, you can design this, and then you upload this, and then the machine will move the camera, and then, so it's important that you rig it directly to the start button. So when the start button is pressed, at the same time engages the camera as the rocket is leaving. You don't want to have a human factor there when someone says 3, 2, 1, ignition, and the guy's, well, we went, whoa. And then everything is wrong.
So then what about the derivative of the acceleration of the rocket? Because the rocket is probably not going to be going at a constant speed.
It's not going to go at a constant speed, but that's what we have is that we have the speed, right? Because acceleration changes speed. So as you add the speed, you don't have to worry about acceleration, right? Because if you have the speed at all times, and we have the speed at all times, you can feed that into the model which raises the camera. So this is a really cool problem. Again, you know, you have the word problem with numbers. You plug everything in, and so this is a design as your ticket to start working at SpaceX. I don't know. Let's do another application problem. Say you have a conveyor belt and you have sand coming in. See you next week. Falls on the conical pile. What happens in time? Oh, before this one. Nope, nope, nope. Delete, 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 delete. We are going first to drink from a soda can. Drink from the soda can using the straw. We want to see how fast is the height of the liquid remaining changing as you are drinking the stuff. So soda can is going to be a cylinder. Let's say, what, 1 inch, 2 inches? 2 inches. And the height is what? 6 inch can. 5 feet. 5 inch. So 5 inch or 6 inch? 5 it is. 5.5. I like the politics behind that statement. Make everyone happy, right? So we have a straw, and then you have some suspicious liquid over here. You never know what you're drinking when you buy those things. I mean, look at that. Can you please lift that up and tell me what, like, is that a real color even? No, it's not even the real color. And you know why that can over there is not see-through? Because we really don't want to see what's in there.
You open up the can,
Oh, no, you have
see
rat.
the liquid
Could
death.
be a rat in there.
Yeah.
Liquefied. Wow, I like that.
That's good, dude.
I'm thirsty again.
No, I'm just trying to see how you get liquefied rat. I guess you get a snake to eat the rat, you wait for it to digest, and then the snake...
No. You take a tarantula and literally just take the rat away from the tarantula, which is like someone else's job. And
I see.
we can monetize this liquefied rat.
Yeah, I mean, see, this is something. This is where the ideas start happening. It always starts in the calculus class and goes from there. So I'm thinking, like, my best idea so far to make money is the powdered water. Powdered water. You say water in a powder. You take let's say you take 1 ounce of powdered water, you add a gallon of water, you have a gallon of water. See, it's invention. They do the same thing with milk and eggs, so why not water? I mean, I'm gonna make millions. I have no time to evaporate all this water to get the powder. But
I'm trying to think. Well, you'd have to use some pretty advanced science, like quantum level, but it might be possible. I think. Biological statistics.
all right, so let's drink whatever is in this can. So what's happening here, guys? Clearly, what comes out of the straw is dV/dt because it's changing the volume in time. So whether we use a straw to suck the liquid out or you put the hole on the bottom and let it drain, it's going to be the same. It's the same concept, losing the volume of the liquid inside the can. So we need to have volume equation. And we see that because we are losing volume, we are definitely losing height, right? That should be common sense as well. So now, what's the volume of the cylinder? What's the volume of the can? What's the equation for the volume? Pi r squared times height. So now we differentiate this in time. Now, how many different variables do I have over here? How many variables, how many constants do I have? So let's go one by one. Is volume a variable or a constant? Variable. Is pi variable or a constant? Is radius variable or a constant? Constant. Nice.
Same for height, right?
Because we have
Radius isn't changing, right? Radius, look, guys, radius is 2 inches everywhere. 2 inches, 2 inches, 2 inches, 2 inches, 2 inches. Which is the reason why I'm doing this problem before the cone. What's happening in the cone? Radius is changing. And height is changing, right?
How about we do
So it's going to be product rule there. But now it's not.
How about we make it a flower base?
That's actually going to be in, it's coming up in chapter 10, Calc 2. Flower-based thing. Look at him smiling, he knows. So, as you have foreseen. And height is the variable again, right? So, when we are taking this derivative, we have dv dt is, and now I have pi r squared, that's constant, and then derivative of h is dh dt. There you go. That's the equation. And all we need to do now is to plug the stuff. We know that the radius is equal to 2. And let's say you are drinking at whatever amount per second. I don't know. Well, this is going to be now in inches cubed. So it's going to be in inches cubed per, let's say, second. So inches cubed per second may be 3. So what do we have? We are losing volume, so negative 3 is equal to pi times 2 squared dh dt. And as you can see, you are getting dh dt from this equation, which is the change in height, and it's going to be a negative number. So it's negative 3 divided by 4 pi inches per second. You don't have to compute that, but that's how much the height changes. So height changes 1/4 of an inch with every sip, right, you take, for instance. So over here, this problem is designed for you guys to think a little bit variables and constants. And here the radius is constant because it's constant. It's 2 inches on any height you consider. Next problem is going to be cone. Cone is also going to have a radius, which is going to be changing now, and the height is changing. So when you take the derivative, we have to do what? Product rule. But before we get and do that problem, which would be the last problem for today, I want to discuss volume formulas. Before anyone starts asking for the formula sheet or something. So we have 3 categories of formulas. We have the prism-like formulas, which are for the cube or the cylinder. That's all objects that look like this. And their volume is always area of the base times the height. So if you look at the cube, this is the base, and then there's the height involved. So those are the prism-like objects. And then you have what I call spiky objects, which would be, say, a pyramid or a cone. Those are 1/3 base times the height, this being the base again. So area of the base. So there are no excuses now that you can tell me I don't know what the formula is.
Wait, what's the third column?
We'll get there. Because all of the shapes, except one, fit in one of these 2 categories. It's either a prism or it's a spiky. Right? Over here, the area of the base could be a square, could be a triangle, could be a rectangle, could be ellipse, right? Could be a circle. Whatever it is, if it ends in spike, you just have 1/3 of this formula. So it's very, very simple to understand all of the shapes, right? You know that the box is length times width times the height. Well, length times width gives you just the area of the floor, and then times the height would be give you the volume of the box. What is alone in the third category? Sphere, the ball. As a perfect object, it has its own formulas. It doesn't fall in any of these categories, so you have to remember these ones on their own, and most likely these are the ones that show up everywhere, including exams, homework, and so on. And that's going to be 4/3 pi r cubed, and the surface area is 4 pi r squared. The other surface areas over there you calculate using the other formulas. So sphere, a ball, is its own category. So now you know all volume formulas. And we used many of these already. So now let's discuss this last problem, which is a little bit spicy, so pay attention. We have a conveyor belt. And we have a sand coming in, dripping onto a pile. Over time, that pile grows. And we know it's a cone if you ever observe the world around you. I would highly recommend you go and get a lot of sand and just do that, right? See what makes. Now, you are not going to hire someone to sit there for most of the day, do nothing, and then push the button to shut off the conveyor belt, right? When it's nearly full. So you are going to design a system that will observe the change in height of the cone, and then when it reaches the certain height, obviously it. Now, one student said, "Well, why would we do this? We just put some photosensors." No, it doesn't work. Photosensors would not work in this case. You got to design something else. So we want to be able to calculate how fast is the height changing, and then obviously when you multiply by the time, it gets you the actual height. So we already know that the cone is the spiky object, which means the volume is 1 cubed area of the base, which is pi r squared, times the height of the cone. So that's the volume equation. And now we are supposed to differentiate that equation in respect to time. But at this point, you have to understand that radius is not a constant, as much as the height is not a constant. So we have the product rule. Here is the radius, and you can see that every red arrow has a different size. So when I take the derivative, I get dv dt is equal to pi over 3. That's a constant, right? You can copy that. But then on the inside, you have the r squared times h. Copy the first, derivative of the second, plus copy the second times derivative of the first. Note that every time when I did the derivative, I followed with a chain because none of the variables are t. They are all either v or r or h. So I have to follow with a chain for each one of them. Now, believe it or not, this is our model. And the issue is that we have way too many variables. How many variables do you currently actually have in this problem, in this model? The one that I know. How many variables do you have? So far, I heard 3 and 4.
Oh, and dv.
Ding, 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 ding. The h dt, the r dt, dv dt, h and r. How many? 5, right? So you're going to have probably a lot of these things given, but not necessarily all of them. There is a very interesting relation which makes this problem a little bit tricky, and that is relation that you get from the similar triangle that eliminates two variables, let's say. Because you know either the ratio of, you know the ratio of radius to the height. That's what you can measure. And you also know how fast the sand is coming in. So let's say that we are looking for dH dt. Let's say that's our goal. Right? You know dV dt because you know how much sand is coming in per minute or per hour or per second. You can measure that. And you can also measure the geometry of the cone. So, if you look on the side, at the triangle, and you realize that the cone was smaller at some point, right? You can get the, it's like initial state where you said when this was 3 feet wide, which was a radius of 3, the pile was, let's say, 8 feet tall. But then the entire thing over here is h, and the entire thing over here is r. So you can write the proportion from here that says that h is to 8 what r is to 3. That's the proportion. And as you can see, you can solve for h. When you solve for h, you get 8r over 3, and you already have something to plug in. Sorry, you're supposed to solve for r because you want to get rid of r. So r is equal to 3h over 8. And the r dt is 3/8 dh dt. So these two equations plugged in the one above eliminates a lot of variables. Well, not a lot, too. Yeah. So it's going to be pi over 3. Instead of r, I have 3h over 8. That has to be squared. And then dh dt, leave it alone. Plus h, leave h alone. 2r, so 3h. So I have 2h times 3h over 8. And then dr dt is times another 3 over 8. Does it make sense? Sure. Whatever, right? So r squared dh dt plus, and the whole thing over here is 2r h dr dt when you plug everything in. So dv dt is equal to pi over 3, and now you square this, so that's 9h over 64 dh dt plus, and now you have your h. H is 9h squared. Yes. Thank you. Yep. Two r oh, I have it up there. I have it here done. So that's 9, 18. Oh no, that cancels to 2. So 9h squared over 2 cancels. So what's that? 324, right? No, 32. Oh, I forgot the HDT over here. The HDT. And if you look at this now, these two are the same. So you can add them. Common denominator is 64. 9h plus 18 is 27. H squared dh dt. Star Wars, no? 27 and 3 cancels. And we get 9 pi over 64 h squared dh dt. And as I said, most of these things you know, you can measure the height of the pile, and then you will be able to figure out how fast it's changing. So dh dt is equal to 9 pi over 64 h squared divided by dv dt. And that's the equation in which you get to plug in numbers. It's, in my opinion, very systematic. You might have a different opinion, but for me, the procedure goes like this. Take a look at the problem and realize, what is this geometry? Is it a circle? Is it a triangle? Is it a cone? So I look at the problem and first get the geometry. I always draw that. And then, once I have that, I know that we are dealing with, let's say, sphere. I immediately in my head know that radius and volume and surface area, those are the things we can talk about when we talk about sphere. Like triangles are the busiest because they have 6 trigonometric functions and a Pythagorean theorem and the area and the perimeter, right? So triangles have a lot of stuff. Sphere, that's it, 2. Surface area and volume. You know those 2 formulas, you can't be caught off guard. So what I do first is I figure out what is the geometry of the problem. Then the second swipe for me is to collect all relevant information to convert everything into mathematical terminology, which means if it says that the area is changing at the rate of 3 meters per second, 3 meters squared per second, I immediately know that's dA dt because area was changing, so dA dt is equal to whatever I said, 4, whatever. And then, so I realize the geometry and I draw that geometry, then I go and collect all the information. Once I collect all the information, I look at the variables that I have and I say, okay, I need a volume formula for the cone or for the box or for the cylinder. And I know all the volume formulas because I learned the cases. And then differentiate volume formula, plug all the numbers in. It's extremely systematic. Every problem is the same. It has different geometry, different approach to modeling, but it's the same procedure every time. Figure out geometry, get the information, see which formula connects that information and take the derivative, and then finally plug everything in there, and that's technically it. Now, obviously all of this sounds very easy when I talk, right? But then you're observing me in my natural habitat, all right? When you go home, it's a different story. So don't get frustrated. Always think these are the layers that I have to unwrap to get to the good part, which means get the geometry, then get the variables and constants, then get the equation, then do the derivative, and then finally plug everything in and solve. So we're going to do more of these problems tomorrow. Let's continue with the lab. We'll do whatever amount tomorrow, and then tomorrow we are going to do 4-1 as well. Bye.